A sum of $5,000 is invested at an interest rate of 5% per year. Find the time required for the money to double if the interest is compounded monthly and then continuously. So we're dealing with compound interest here. So our formula for compound interest is A of t, the amount after time t, is P, the principal, times 1 plus R over N to the NT. In order to solve for time t, to solve for an exponent, you need logarithms. So let's go and plug in everything that we know. First, we know we're trying to double the money here. Okay, so if we want it to double, that means that this A of t is $10,000. Okay, that's double what we started with of 5,000. Okay, P of course is our principal. That was just given to us in the problem, and then we have 1 plus R is the interest rate, and that's given to us as the 5% per year. So in decimal format, that's 0.05. And then we divide by the number of times compounded per year, and we are doing monthly compounding, so that's 12 times per year. And that's to the 12 times t. So now we're just trying to solve for t. So we can divide both sides by 5,000, and that gives us just 2 equals 1 plus 0.05 over 12 to the 12t. Now, to solve for an exponent, we're going to use a logarithm. And because I'm probably going to want an approximate answer here, since I'm going to want to actually know how much time it takes, we're going to use the natural log because we know our calculator can do that. So I'm going to take the natural log of both sides. I have natural log of 2 equals the natural log of 1 plus 0.05 over 12 to the 12t. And the reason using logarithms is nice is because now I can use my exponent rule that says that I can pull that out in front. So I have natural log of 2 equals 12 times t times the natural log of 1 plus 0.05 over 12. Now I'm trying to solve for t, and so I just need to divide by 12 and by that natural log. And so I end up with t equals the natural log of 2 divided by the 12 and the natural log of 1 plus 0.05 over 12. Now we're ready to just go ahead and plug this into our calculator. We've got the natural log of 2, and we're dividing that by, and I'll use parentheses here to be safe, 12 times the natural log of 1 plus 0.05 over 12. Close parentheses on the natural log and close parentheses for the denominator. Hit enter, and we get, we'll round this to 2 decimal places, 13.89. 13.89. And of course, this is going to be in years since our rate was measured annually. And so this is in years. So almost 14 years that it takes for this amount to double. For part B, we're looking at continuous compounding. And so our formula here is A of t equals P times E to the RT. So everything is the same here. A of t, we're wanting to double, so this is 10,000. P is the 5,000 that we're starting with. E to the R, 0.05, and then t. And so we are now doing essentially the same thing, trying to solve for that t. So we can divide both sides by 5,000, and that's going to leave us with the 2 on the left side, just like we did in the previous part. So 2 equals e to the 0.05 t. Now I need to get rid of this base e, which we know we can do with a natural log. So we get natural log of 2 equals 0.05 t. And then we can divide both sides by 0.05. Okay. So we have t equals the natural log of 2 over 0.05. Of course, we'd like to get a decimal form for that. So we can plug this into our calculator. Natural log of 2 divided by 0.05. And we get 13.86, round to the nearest hundredth there. So 13.86. Notice that it takes a little bit shorter amount of time if we're compounding continuously to double than it did when we were compounding monthly, which makes sense with our intuition of what it means to compound continuously and what that means for how fast our investment grows.